very much for inviting me to participate in this event. I participate in a study, theoretical study, using a Monte Carlo simulation of the dose deposited with secondary particle appearing with high photon energy in radiotherapy. Of course, this work was published in a journal article, and I present here a resume of our work, prepared by Mustapha Assalmi, and in collaboration with Professor Al-Yamani from Laboratory of Biology, Geoscience, Physics, and Environment, multidisciplinary faculty of Mohammed First University, Jeddah, Morocco. So the objective of this study was to investigate the Monte Carlo simulation behavior of the contamination particle appearing with high photon energy. So we study here an example of the breast treatment, and we tracking the contamination particle appearing with this this beam of 18 megavolt emitted by electron accelerator. So the near phantom modelized was based and the Monte Carlo simulation, of course, was based in G4 unique MT code. Of course, each component of the medical accelerator use it, modelize it in Monte Carlo simulation, use it and real dimension and material construction of each component. Based on the agreement signed with the company Electa Synergy and Electa company to providing us the information about the Electa Synergy in opportunity installed in our center Oncology. The agreement allow us to use the real dimension in the material construction of each element in the head of medical accelerator. So for Monte Carlo simulation, we base it in G4 Linux is a code developed by a Moroccan Jafar al-Bakali. This code programmed in C++ and has an interface graphic based in Java. This code, of course, we have validated in simulation of Electa and other medical accelerators such as Varian and Saturn. This code has a three module: the G4 Linux head to construct the geometry of medical accelerator and to simulate the phase space of the particle emitted in the medical accelerator head. And other module, G4 Linux those scan to calculate the dose deposited and those accumulated phase space. And other module, G4 Linux data analysis to analyze the data in phase space and in those scan. This code has advantage of very optimized in simulation time because based on the multi-threaded technique to achieve a high accuracy in the Monte Carlo simulation. Of course, this could necessitate a high performance of computing. For this, we use it HPC Marwan, high performance computing Marwan grid connected to the Marwan network with a grid Moroccan grid with high capacity, which allow us to simulate the Monte Carlo to achieve a high accuracy in Monte Carlo simulation. For those measurements, we have used the IBA-CC, a ionization chamber in measurement dose distribution in a water phantom, and we use it in water phantom EW type, and the software make access to acquisition of the data. The measurements carried out at our clinical oncology Ashark Clinic Ashark in Oujda, Morocco. Of course, the first step we have validated this could be multi-color simulation in standard example of water. The multi-color simulation, the results of multi-color simulation has a good agreement with the measurement in PDD. The analysis here of the agreement between multi-color simulation and experimental measurement compared using the gamma index fixed at 2% over 2 millimeters in two fields, 5 in 5 feet squared. Of course, in multi-color simulation, the problem was in the build-up region. I have a paper disputing this problem of divergence between multi-color simulation and experimental measurement, because here we detect the charged particle which affect the accuracy in the dose. And also, we have used a cylindrical ionization chamber which has a high size and not recommended to accurate those in the built-up region, and for also in the B-number region for lateral distribution. Here also we have the validated with good BMX experimental measurements in lateral dose distribution. The results has a good agreement between multi-color simulation calculated by G4 linear MT and measurements measured by EBA CC13. The validation was in three fields, 5 in the 3 in the 15 square field. The analysis, of course, by Z and the gamma index fixed at 2% over 2 millimeter criterion. This table resumes the comparison between multi-color simulation and the experimental measurement in the water for validation with simulation of our work in PDD in profile, this dose distribution. The comparison are basically mean absolute dose error. It is clear in this table that the agreement is high in between multi-color simulation and experimental measurement in all the field. And also the most field simulated has a good gamma index criterion. Also, we detect our, we achieve now our objective to detect the contamination particle appearing with high photon energy. So for high photon energy, we detect 4 types of particles. Here we detect electron, positron. As you see, for energy, for photon of energy over 10 MeV, we can detect other particles as neutron and the proton. This particle, of course, was created the interaction between the photon beam and electron component. This particle, of course, was not planified in the system of planification TPS, and sometimes has a significant effect and significant dose in the accumulated dose deposited in treatment. So, of course, our objective here to tracking this particle in the example of nerve phantom positioned and adjusted in the same condition of the treatment by radiotherapy. So as you see here, we have 4 types of particle detected in the end of the electron synergy head accelerator. Here we show here the origin of the creation of this particle in the LINAC component. Multi-color code G4 LINAC LT allow us to know the origin of each type of particle crossing the phase space. The most important information here in this table is neutron therapy, neutron particle, because for electron, positron, and neutron is not important, significant dose in the radiotherapy, but the neutron has the most important here in high photon energy. And the most information indicates that the neutron was created in the gel and MLC collimator and the primary collimator. This indicates that the majority of the neutron was created in the end of the component of the LINAC, in the blendage of the LINAC. This can allow for neutron to deposit those outside of the field. Of course, to demonstrate this, we have simulated those deposited each type of particle in the water phantom for several radiation fields in depth and in lateral, in depth here and lateral distribution. This figure shows the those deposited by electron, positron, and neutron, proton. The information, the most information here in this table, that those deposited electron, positron, and the proton decreased with depth, and for neutron, those increase at the maximum value in the depth and decrease it exponentially, and can achieve a depth in a water phantom and can achieve a 35 centimeter. And for the small field, the maximum dose was noted in the small field. That probably can justify the hypothesis that for small field, the irradiation, the gel are closed. And we have demonstrated in the table that the majority of neutron are created in the gel and MLC. For this, in small field, because the gel are closed, and we have a supplementary energy photon created in the component. This hypothesis was demonstrated for the lateral dose distribution. As you can see here, for electron, positron, proton, the dose located in the interval of the field. The field here was 15 centimeter square. And for neutron, the dose lateral is almost linear. This indicates that have most dose and significant dose out the irradiation field. Other particles are located in the interval of the irradiation field. So we have modeled a mirrored phantom of male human phantom to simulate same condition of the breast treatment using high photon energy. Despite this, beam is not used for breast, but we can demonstrate the transfer of particle if we use it, the situation of the breast treatment use a high photon energy. We positioned the phantom in same position as real treatment, and the mirrored phantom was modeled the G4-Linux AMT using script language, and here the position, the angle of gantry in the same used in TPS. And the result of spatial distribution of photon in function of its kinetic energy at the surface of each organ as indicated in this figure. I noted here, we not calculate the absorbed dose, not absorbed dose, but we detect the dose at the surface of each organ, not absorbed dose. In our in current work, we try to calculate the dose deposited with this particle. And for this time, we have simulated the tracking, we tracking the transport of particles at surface of each organ of Myrt phantom. And here, for neutron contamination, we can see clearly that the majority of neutrons are located in the field and the arms, right arms of Myrt phantom. And here we resume the number of neutrons and the main energy of neutron contamination appearing with high photon energy in each or at surface of each organ. It is clear the majority was in the skin and ribs, the number of neutron, and in the legs. For a high main energy neutron contamination, of course, is located in the field of radiation of the breast and also in the thyroid volume. To conclude, the contamination particle detected in the phase case for 18 megawatt day are electron, positron, and neutron and proton. The majority of contamination neutron are created in linear component of high density, as we see in MLC gel and primary collimator. The contamination neutron are able to deposit at those depth and outside the irradiation field. The kinetic energy of photon in the left breast irradiation field of Myrt phantom reach about 3.5 MeV and about 0.5 MeV for contamination neutron. And the large number of neutron is captured at the surface of cage and the legs of the Myrt phantom position in adjacent in treatment of left breast. The high main energy photon neutron is captured at the surface of the left breast and thyroid of Myrt phantom position and adjacent of left breast treatment. Our current study, we try to simulate aerial phantom of Zubel phantom developed in the Germany's laboratory. We simulate here the dose deposited, the contamination particle appearing with proton therapy in Zubel phantom. We try here to estimate those can deposited with this particle created in geometry of the VNAC. And thank you for your attention.